All right, good evening. My name is Nino Ripepi. I'm an associate professor in the Department of Mining and Minerals Engineering at Virginia Tech. I've been in this position, or I've been working at Virginia Tech in this department since 2012. Um, and I'm going to talk a little bit today. I've called it high-tech mining engineering. I'll talk about automation, drones, and a little bit about data analytics, things that we're doing within the mining and minerals engineering program from both the teaching side as well as the research side. Um, so the question really is, mining engineering. Have you heard of mining engineering before? Um, when I came to Virginia Tech back in the 1990s, I'd say I was a third generation coal miner. My father and grandfather both were surface coal mining operators in Pennsylvania. I came to Virginia Tech not knowing there was such a thing as mining engineering. Went through a bunch of different open houses similar to this, different meetings with professors and students, and I just felt at home there. I was an engineer who got to work outside. I really like the outdoors. Got to solve a variety of problems. A mining engineer works on mechanical engineering issues, civil engineering issues, chemical engineering issues. Um, a mining, and when we think about a mine, you're digging a hole either underground or from the surface, in recovering a mineral that's in place there. You need all kind of different types of disciplines to get that work done. There's a picture of me working on a natural gas well, which is associated with taking methane, an explosive gas. It's dangerous for health and safety for out of an underground coal mine, and actually producing natural gas and selling it. Right. So it's a project I worked on as part of my dissertation. Um, Other reasons to look at mining engineering. There's lots of scholarships available, lots of jobs. And if you're into sort of the energy, for me, that's why reasons I looked at it as a freshman at Virginia Tech. But also I had a passion sort of for energy research, and that's led me through my career. Well, I'll just kind of talk about what mining engineers do. We produce raw minerals and energy resources needed by society. So metals, industrial minerals, construction materials, energy, critical elements. So everything you're using in your phones, there's lots of gold, um, other critical elements that end up in sort of phones, in renewable energy. Right, we need a lot of these critical elements for solar panels and wind turbines, construction materials. Everything you see every day that you're building, all the building materials you use are mined. Right, industrial minerals, diamonds, other things that are used in salt, titanium, those sort of things, are all mined. A lot of energy resources are mined as well, like coal, to oil and gas sort of things are sort of mining. We take it from the center of the earth, right? Um, so we're considering these mined materials. And these are things that we research, we teach about. Our students go work in these operations all around the world, right? So where these resources are used to make or support just about every sort of tangible human effort. We say it's you either grow it or you mine it. It's basically two different ways to get things, right? So mining is, some people may think of it as sort of I'd say like a dying industry. Absolutely not. I mean, we think about renewable energy production, the amount of material that we're going to need to transition from a fossil fuel based energy sort of economy to a renewable one. We're going to need to mine a significant amount of materials to produce the rare earth elements that are used in these solar panels, right? For example. So, you know, mining is not going to disappear. There's too much demand in the world today. And the resource deposits, they're they're everywhere, right? All over the world. Let me get this to play. Yeah, they're just, when you think about different types of minerals, we saw in the previous slide, these types of minerals are showing up all over the world. So there's jobs everywhere. Mining engineers are working, I mean, I guess in 6 continents, maybe not Antarctica, but all over the world. We've become involved in sort of a range of different activities, from exploring, finding out where these minerals are, to figure out how to get them out of the mine, designing the mine and the mine operations. So, in mineral processing as well. So, I would say most of our mining engineers end up in either the mine design phase, the mine operation phase, actually doing the mining itself, or in processing the minerals, right? And then we do also reclamation, monitoring, mine closure. So that's sort of the full cycle of mining. So there are, mining and exploration. We can go out and look for minerals. You know, even up in the Arctic in different places, or in your sort of backyard of Burke, Virginia, or wherever you live. We're looking for deposits for construction materials, right? So aggregates. We're doing a lot of reserve estimation of where those are located. What are the quality? That's pretty commonly done. The scope and scale mining projects mean that a host of career paths are open to engineers, right? You could be working in mine design. So there's a big a big open pit mine that we're trying to get to the material there. We could be working in mine operations around a lot of equipment underground here, doing surveying, environmental management. That's a really important part of mining. Mineral processing. Actually, after we get that rock, break that rock into smaller pieces and get out what we're looking for within that rock, and then equipment as well. So we have a lot of people that go into the sort of equipment, the equipment arena as well. So those are just a little bit about mining engineering. I'll come back to that sort of at the end. If you have any questions, Grant, let me know. As we go, you're welcome to jump in on the chat or just, ask me right now if you have any questions, sort of, where do mining engineers go to work? Where are people getting jobs? I can answer that now or sort of at the end if you have any, if you're curious.
I don't think I have any questions, honestly.
All right, cool. Yeah, so hang with me here. So with regards to what I wanted to talk about today, this is a project that I'm working on here with Richard Bishop. Right here is a picture of Richard. He's my PhD candidate that works under me here on research. He has, I think, 2 degrees at Virginia Tech in mining engineering. He's working underground in underground stone mines. See a picture of this underground mine here. And he's doing both 3D photogrammetry as well as LiDAR, which is like laser scanning underground, through both sort of handheld on tripod surveys as well as drone-based surveys, right? So you can think about sort of not the advent of utilization of drones, but sort of recently in the last 10 years, drones really becoming something that, anyone can buy really off the shelf and go fly and take pictures from or even run some missions as well if you have a GPS sort of enabled drone, right, about here. So if you get a one that has a sort of a GPS on it, you can program that GPS on a smartphone app and have it do sort of weigh missions above you at certain elevations, right? You go up to 500 feet, fly a grid, come back and land in the same place, right? So you can program those sort of things through GPS. We go underground here, it's a little bit of a different story. There's no GPS underground, right? So how do we explore underground? How do we map underground? So I'll talk a little bit about how we're doing that on this project. Just thought it was an interesting project that we're doing that's sort of applicable. So this is the mining that we went in here. It has here's a 30-degree dipping deposit from the surface. So you can see this is under sort of a mountain here, so it dips underground. These are all the openings that the mine has developed over 50 years. It's an underground limestone mine. It's dipping at 30 degrees. It's a 100-foot thick seam that's dipping here. So this is how you can see, this is a picture, I think it's from a drone. Yeah, from a drone up in a 100-foot tall opening underground. So we're mining limestone that's utilized for chemical lime industry. So they have a kiln there and they produce a chemical lime that's used in the chemical industry, and for a bunch of other uses as well. So it's room and pillar mining, meaning that we leave these pillars in place. So here's a picture sort of on the side of a pillar. These are the openings that were mined. This is LiDAR scan here. This is the pillar that's left in place. So you can see just series of pillar after pillar to basically support the roof, right? So you can see we have at some places we're almost 2,000 feet deep under this mountain. Imagine these pillars have to be pretty large to support the roof so that you're able to mine and move around in this mine, right? So it's pretty important, the sort of roof support from what we call ground control reasons for health and safety, so we can mine efficiently. So designing these pillars, how big they can be, is what we work on every day, myself and my students, so that we can optimally recover and safely recover the reserves we're looking for. Go to the next one here. So it's traditionally, this is how we've done surveying underground. We've had or theodolite or some sort of total station underground that we're using. Surveyors are going around. It's pretty slow. It's proven. It's very precise. Takes lots of time. You're walking around taking point measurements. There are some hazards. You look underground, there's rocks, there's, slip and trip hazards. You're doing this all day. You could put yourself in some uh, dangerous positions here with regards to rocks potentially falling on you or whatnot. So we're thinking about going back into areas that we haven't been into in maybe 50 years or 10 years or whatever it is, maybe a year. We want to go back and explore an area, or we want to go change where we're mining. It's a little dangerous to go into some of these older mines because they haven't been properly scaled, properly. The ground hasn't been properly bolted and controlled that we typically do. So maybe this isn't the best option, right? So LiDAR as well. We use LiDAR on this. It's basically a laser scanner. It's taking a laser. It's hitting a hard surface and coming back to the laser. Right, this is going very rapidly, and we're creating a 3D mesh cloud of the distance away, right? So that we can create that surface. I'll show you some pictures of that coming up. So one option that's a little bit cheaper than LiDAR, that's why I said LiDAR could be cost prohibitive, and we have a LiDAR system that's $40,000 that we use. You can just take photos. You might have seen this, or you might have seen an app on your iPhone or whatnot, where you can walk around an object. You can do this at your house, right? You can walk around, take pictures from multiple angles of the same object, and basically the computer program will stitch those together and basically mesh them, right? Especially if you have like known places or known sized objects in there. So that's what we do. We put different sized balls and whatnot into our photos, different places or rocks. We'll mesh these all together. We have overlap, and we're able to create these 3D meshes that are basically a 3D object, 3D photo. And then we can bring that 3D photo into into any sort of program we want for, different things. We actually characterize the rock, the joints in the rock. We look for hazards, rocks that could fall. We could use it just for mapping purposes. So we do that on tripod. We can also do it in drone based, right? So we're doing both of these things. So here's a mine pillar that we just walked around. So we want about 60% overlap. So we take a picture, walk, take a picture, walk. It's really important. The lighting in this is very important. So we spent a lot of work on LED lights that we can get underground on tripods to take these pictures. So these are all the sort of pictures we take in our process to go to capture and aligning those and creating this 3D mesh. And here's a sort of video of what that solid looks like, this mine pillar, right? We walked around. So pretty cool, pretty useful for it take us 20 minutes to walk around this pillar and take the pictures, feed them into this is called Agisoft software here, feed it into there, mesh it in a certain amount of time, not too long. And then you have this 3D image. So you could send this around the world. People could be looking at it. Other mining engineers or people could be evaluating, these pillars. Is there ore in there that we want to recover? You have a question, Grant?
Yeah. So what do you do with these 3D models? Like, what's their primary purpose?
Primary purpose, right? Sure. So there's there's multiple purposes. I would say the first one is I'd say the most important is if you go back to that picture before where we have 100-foot tall pillar, right? If you're trying to look up from the ground up 100 feet, you can't see anything up there, even with big flashlights. So when you're in an underground mine, it's really important what they come in here. And maybe I should just go back to another picture. Let's go to this one. Is they come in here with a scale or bolt different rocks up for support, because you don't want to. If you have a rock that's even the size of a football fall from 100 feet and hit you on the head, it can kill you easily, right? So they want to knock those rocks down, identify where they are. If they're really big and look sort of loose, they'll put a roof bolt in there to anchor it. So they'll put a 16-foot roof bolt through that rock into more competent rock. Or they'll come up with a big scaler that has a claw. I think there might have been a picture at the beginning that knocks the rock down, or people go up in big cherry pickers with pry bars and pull rocks down. It's hard to see a lot of these things. If we could make this 3D visualization, I mean, you could just go walk around the mine, and we've done it in virtual reality as well. We brought this stuff into VR, where we're using like the HoloLens and some other VR platforms, where we could walk around in these mines and look for hazards. That's probably number one. Number two, we could create maps, realistic maps out of these areas that would maybe be a little bit quicker to do than if you were doing it with a little bit more precise total station sort of thing for surveying. So those are two of the reasons people were thinking about looking at taking those photos. And you wouldn't necessarily need a 3D photo, but the 3D photo lets you to create a volume as well. So we know how much material's in that pillar, right? So this pillar, let's say we go to a lead zinc mine, or something where the ore that's in that pillar is worth $1 million, let's say, right? And we've already mined everything. It's pretty easy to get that out. We could drill holes across it, load explosives in there, we blast it, the rock falls down, we have all of this ore then that we scoop up and take out of the mine that's worth upwards of $1 million in some cases. If we were to, the issue is from the sort of ground support. If we took a pillar out, all the surrounding pillars would have to take that load on, right? So when you walk out or leave a mine, sometimes people will do that as they're leaving the mine. They'll start taking some of the pillars out because of the amount of ore that's in there. The people are in a safer area behind that. They'll blast it, then they'll come in with some sort of remote control or autonomous loading and hauling trucks that move that material out of the mine. So there's a lot of money there. If we had to decide on it, though, we could use the photogrammetry to look for the ore, try to calculate it, put it in a sort of 3D thing, and then decide if that's one of the pillars we want to take out. So that answer your question?
Yes, that's very helpful. Thank you so much.
Cool. Yeah. So here's some pictures of a drone-based survey that we did. As I mentioned, I got 3 graduate students working on this project here. You can see how big these pillars are and the drone flying underground. Once again, we've got this thing really lit up with all kinds of crazy lights to try to get these pictures. You go in there and turn your lights off, it's pitch black, right? You can't see anything underground. There is no outside light coming in there. So we need to bring our own lights. So we're putting lights on the drones itself. We're using LiDAR a lot, as I mentioned. That doesn't matter if there's something already lit up there. You don't need light to run that. But we're able to see up into these areas that are upwards 100 feet tall, right? I mean, from the ground there, it would be very hard to see the rocks, specific rocks. So that's the reason we're using some of these drones here. So here's some of our, I think is a quadcopter we're using with a company called XN Technologies. You can see on there they got a LiDAR puck. So this is made by Velodyne. It's about $8,000 LiDAR system, and it's rotating. I think I might have a video of it, but it's rotating 360, and it has about a 270-degree angle that it can take LiDAR measurements. So basically distance measurements from wherever it is. And it's got a computer on board, system here that is processing that data, sending that data back to a handheld sort of tablet, and that tablet's actually mapping things in real time, right? It's calculating where the drone is, and it can do that basically in real time. So it's pretty awesome. I'll show you some of that. Some areas that you can't get to, like we couldn't walk up this. This is too dangerous. Couldn't go up there through these openings. They're too small. Drones can do that. So we're a lot of drones that you buy off the shelf will have some collision avoidance systems on them. Most of those are camera-based systems. We're using LiDAR-based systems, so we can bounce. We're going to calculate the distance in multiple directions from a surface, right? Through a LiDAR, the laser goes out, comes back, and we can then program it and say we don't want to be within 20 feet or 10 feet of the roof or the ground or a wall, so then it could stay that distance away, right? And then you can program it to stay in the middle of distances when it's calculating multiple directions. You can do all kind of different things. So working with computer engineers and designing these systems is pretty neat. So here's another survey here. Looking at the drone that this is the one we built in-house here at Virginia Tech. It's got a couple GPSs here. It's called the Alster LiDAR system here. We're using these for methane monitoring as well. So sometimes we put methane sensors on these. We're flying these over pipelines and gas compressor stations, looking for methane leaks. So we're kind of using drones for all kind of different things. Yes, there's just some videos of the drone flying, and as I mentioned, it can get into places that are sort of inaccessible. And this is photogrammetry that we did here, um, from a drone based, flying this around the pillar. We're able to take the pictures off the drone and then use that to create our 3D sort of uh, pillar here. Right? So kind of cool. Yeah, as I mentioned, LiDAR. So this is the LiDAR working here. You can see it rotating 360. So I mentioned it's got 270 degrees of coverage, plus 360. So it's almost seeing the whole, almost seeing everything except right below it in this case. So it's trying to map everything. So here's some images of the LiDAR. So once again, these are just point clouds, right? So we don't have we don't have the photos behind it, right? So this is all from just what the structure looks like from the LiDAR, right, itself. And you see it's pretty cool. As you can see, it's gathering, millions of pixels every, few seconds, right? And this is as I mentioned, this is the system here where we're sort of watching this in real time. So this system here is called the system's called, but the sort of the idea is called Simultaneous Localization and Mapping, a SLAM program, right? So we're constructing a map of an unknown environment and positioning of the object within it. So this is a picture of the drone flying as it's bouncing the LiDAR off. It's creating this mesh network, right? It knows where it is to start, and it's creating this mesh network as it's taking these repeated surveys. So it can go into an area and explore, right? It's triangulating everything here as it's taking different shots of the same cube basically, and it's fixing itself so it knows its different pathways, so it could actually go explore into a mine in an area you don't want to go, right? It's either too dangerous, you're not sure, you've never been there. Let's send a drone in first. It's going to map itself in. It's going to go in for 6 minutes or whatever whatever we program it, and then it's going to know to turn around and follow its breadcrumbs basically back out from the map that it created, right? That's how we've programmed these. So it can go in, explore. We always want to make left turns. We always want to make right, or we want to go a certain distance. You can program it to do these things. And then once again, it's at a certain time. The big issue with drones is basically the battery life, right? So these have 10 or 15-minute battery lives. At some point, it's going to have to turn around and come back home, right? So this is called simultaneous localization and mapping. So here's a picture of this drone here doing this autonomous basically mapping. We're here, we're not, we're letting it go. We let it go itself. It's going and doing the mapping. It's going to go a certain distance, go around pillars, go outside of radio communication, and then basically return home. So here's a picture once again of this sort of LiDAR mapping. So pretty neat technologies that could be used in going into mines that you haven't been in 50 years, right? Do you really want to go down in that mine? You're not sure what's going on. Let's go send a drone in first, right? We're also thinking about using these, and I'll talk a little bit here later, is about for mine rescue, right? We do a lot of health and safety in mine rescue, and if we had an issue underground where we needed to send people in to try to find other people, well, maybe that could be dangerous in itself. If the environment's bad, we can send a drone instead. We would much rather send a drone instead of risking someone's life, right? Yeah, here's just some more videos and pictures of the sort of drone flying here, and these are our lights we put on these tripods to get these video of the drone working here. So we're building these things because we want a certain payload. We've got a couple kilogram LiDAR system. We want to put cameras on it, different sensors, little computer system. These drones are starting to get bigger batteries. So we're going to quadcopters or hexacopters or even 8 sort of copters, trying to carry a big, pretty decent sized payload for an extended period of time. So, Yeah, there's some more flying around. This is some of the equipment underground here. So you see a still shot of it. This drone's able to fly this LiDAR system here, and this drone created this map then. So you can kind of see these two pieces are those. This right here is this right here in the map, right? So it's created this 3D map by just flying around and just let it run there. Yeah, so you can do this in real time, right? That's what's pretty cool about it. We actually took, instead of flying the drone down, this is that mine we went down. Remember, it was 30 degrees dipping underground. This is the drive. I mean, we're basically driving a car or truck down this um, through these openings here. It's just winding back, it's spiraling down, right? So we're spiraling at a 18-degree slope, and we're going down 1,000 feet underground. We're able to drive down a truck through these roadways. The question was, could we map this? These have been here for 50 years, some of these openings. So we were going to fly the drone down, but that would take extended period of time. We just took the drone and basically attached it to the truck, right to the front of the truck, and just ran our LiDAR system. The drone wasn't running, but the LiDAR was running to create these maps of the mine itself. So it was sort of mobile based in this case, right? Here's a video of us, and it's creating it real time. You can see this is what this SLAM system is doing as it's going underground. It's creating real time maps. So you can see this on your tablet if you're in enough proximity where you're downloading the data from the drone. So we got a Wi-Fi sort of mesh network on the drone. We're sending that data back to a tablet in real time. So this is us driving and mapping basically in real time, going underground. So it's picking up different cross cuts that we have, but it's not exploring them totally. So you'll see at the edges, we will have a lot less density, right, of points, because we didn't actually drive there. We were driving on this part here, and it's taken shots into those other cross cuts and openings. So we haven't mapped the whole mine. We were just mapping the main tunnel that you drive down, and it's picking up some of these cross cuts because they're in close enough proximity. But the density, as you get further away, your lasers will have less and less density, right? So you want to be sort of at an optimal distance away from the wall in order to get full coverage, if that's what you're sort of looking for. So I thought this video was pretty cool. Just let it play there. Yeah, so you can see this is where it thinks the drone was, where the LiDAR system is. So we're actually following it now back inside the 3D mesh cloud here. So this is sort of pulling back out, looking at everything it mapped, in 10 minutes, right? If you tried to survey this, it would take you days to do anything like this. And this was done driving underground in 10 minutes. Other reasons we're doing it, this is really important, is geotechnical characterization, right? So I'm not going to go into this in this presentation about what we're, sort of all the modeling work that we're doing, but we can map joint sets, discontinuity. So the rock itself, because the way it was deposited, the way it's formed, the way waters run through it, it's creating these surfaces, basically, where two different rocks have planes that connect to each other. So we'll have a joint set here where you might be able to see sort of a bands going this way. You'll see different rock structures that are be popping out here. We can take these laser scans or the photogrammetry and map these discontinuities. So we can map the planes basically. So you can see all the different planes we're mapping here, the direction of them, the width of them, the aperture of them. And we can use that information this geotechnical information to go into a model to see how strong is this pillar, right? Will the pillar fail under a load of 2,000 foot of rock? What's the risk of that pillar potentially failing, right? Are we over designing, under designing? We want to know that. So we need to take these inputs from the rocks into those models, right? So we do a lot of pretty sophisticated modeling work to see how the stresses and strains on these pillars, how will they react under different loads as we excavate the ground around these pillars. So here's another sort of video here looking at the laser scans that we did. These are done by hand, not by drone, but you could do the same thing. And we're mapping all these different planes in here, right? So we have all these different, in this case, we have 4 different, what we're calling joint sets, 4 different directions, dips. And there's different distributions of those and how many fractures there are. So what's really important is as we have these different fractures that cross each other, we're creating blocks, right? And these blocks, once again, can be really large. And if these blocks become loose, they can fall and hurt equipment, hurt people, um, cause issues with the strength of the pillar. So that's another reason we're doing this. Change detection is really, pretty important, could be very important. So we can look over time, right? If we did different surveys over time, we can look to see pillars changing shapes as they take load. Can we predict failure then? This is, looking at a picture versus a laser scan going into this mine opening. There's a drone flying here. We can mesh these two together. We can overlay pictures over the laser scans. So then we can both visualize it really well with a picture, but be really, really accurate with regards to the laser scanning. So we're working on overlapping those. But then if we just keep taking pictures every time we come into this mine or every week or every month and compare it from one to another, we can then do sort of a hazard map. And things in blue have not moved. Things in red, we've seen significant movement, right? So by seeing this movement, then we can identify these are potential hazards. There are rocks moving. Maybe the rock already fell. That's why we see a lot of red. But if the rock's moving or the pillars are changing sizes, they're getting, we could predict failure, right? So change detection is one thing that we're really looking at. You can see this. There's people up here on this big fall, and this is where this drone flew through here. Other things we're working on is sort of meshing these drones, right? So the biggest issue, as I mentioned, was battery life getting into a mine, especially if we're exploring or if we're doing the things from search and rescue, looking for people where there's a mine disaster. Can we send small drones in that work as a Wi-Fi sort of mesh network where they can just sit down and they have enough battery left when they sit down to basically be a node where they can transmit data back and forth. So we could drop these all around these pillars, these cheaper, smaller drones, and we can bring our big drone in later and it can talk to these networks and it can follow them around and it can relay its data back as it gets further into the mine, right? Before maybe it sets itself down, depending on how you're designing these things. For $100, we can easily put together a drone like this with a Wi-Fi mesh on it where it just sits down. We don't even need, you don't need to recover. You're not putting in $4,000 drones and dropping them, right? We're putting $100 drones in, and we could be dropping them different places and maybe recover them later if we can get into the mine. If we can't, it's not as big a deal. So I think it's we can extend the range of these drone lives because they're able to follow more quickly rather than mapping as they go as well, right? So we could send one drone in to map a certain distance, come out. We can send these smaller drones in to set a Wi-Fi network up where the next drone kind of sort of goes much quicker and follows it through. So, there's lots of different ideas we're sort of throwing around here with Wi-Fi mesh. So, conclusions, we're doing this. The main reason we're doing this is risk mitigation. We don't want people to get hurt underground. It's dangerous for rock falls on a person here, right? We're doing this for faster data collection than we've done historically. We can vastly improve visualization, 3D modeling. We can do inspections in difficult or previously inaccessible areas. Places we didn't really want to go into, we can send a drone into there, right? We can do hazard identification assessment in these risky areas, especially older areas, right? That's sort of one of the big goals is to get into those areas. So that's what I had on drones. I got a few more slides sort of on mining at the end here. But while we're here, you guys have any questions about sort of drones underground or Sure, if there's a drone in this picture, there must be one somewhere flying. I don't know. Maybe not. Maybe just, as I mentioned, these are these roof bolts here. It's hard to see them, but these rocks are bolted up um, in these openings. Um, where we do a lot of this. Is you see this mesh up here? This is a karst void. It's basically rainwater that's dissolved out limestone over millions of years, creating these voids or mud cavities underground. We're doing sort of ground penetrating radar, looking through the rock to try to find these openings. It's one of the applications that is pretty neat. We've flown drones up into openings as well, like into these karst voids that are only a couple meters wide. We'll fly drones up there and they're able to map them. How many mines have you implemented this in so far? Well, we're working with a company here, we're called XN Technologies. They've probably been in 100 mines. Ourselves, we've probably been in, like, I'd say 3 or 4 mines working on these technologies. So we're doing some stuff in house. We're working with some people in computer engineering, and we're working with other companies to try to get these designed and implemented. There's only a handful of companies really doing this worldwide right now. I expect this to increase significantly, especially some of these metal mines. They've got the way they do the underground mining. They're creating these underground caverns that you can't send people into. They don't know what it really looks like in there in some places, the way the mine's designed. So they fly drones and they can map those areas out. So that's where a lot of these applications are heading. But yeah, it's rather a few years old sort of technologies that are um, uh, basically coming to be finally. Any other questions?
Yeah, I have two. I don't think they relate as much to drones, but just about the mining engineering
Oh, cool. Yeah, go
program
for
in
it.
general. So, first off, I take it this is a fairly small program, like not a lot of people in it.
Yeah, so I mean, in mining in generals, yeah, pretty small within the country. There's like 14 other mining engineering programs in the country. We typically have, depending on the year, we've had, I'd say the high was probably, I think we had about 80 students in a class. More typical is the 30 to 40 range. We've had down to 20 in a class. So we're typically in that 30 to 40 range, which makes for you get to know everybody. It's a pretty small department. You get to know all the professors really well. We've got, I think, 11 faculty. So yeah, it's one of the smaller programs at Tech for sure. Yep. But it's pretty intimate, and you really get to know both your classmates as well as the professors. I'm not sure if I talked much about internships. Everyone basically interns, and hopefully we recommend 2 different summers at 2 different jobs if possible. To get experience, both maybe underground or on surface mines, wherever you can find a job. We bring a lot of people in to recruit. We've got about 100, I think we have 100% job placement the last couple of years. Starting salaries, I think 65 to 70,000 a year. Starting salaries with really good placement. With regard, I mean, if you do good grades and do a lot of other things, you have no problem. You have multiple job offers. But if it's got to be like a match with this is what you want to do. Do you want to work in a mining environment? So that's, it's good that you're here for sort of first step to see if this would be something that interested you. Does that help?
Yes, that helped a lot. Thank you.
You said you had another question, or?
Oh yeah, you just answered it. I was going to ask if you happen to know the median starting salary for
I think
people
it's
just coming out.
Yeah, I think it was 65 to 70 last year. I think in that range. That's what I've been told, at least. So let me go through a couple more things on mining. So maybe that'd be maybe it'll help answer something. So this is a little video here, just from a couple of our recent graduates, them talking about what they're doing. So I thought that'd be useful.
An engineering degree from Virginia Tech opens up many pathways, not only with the number of companies you recruit at the school. The name carries a lot of weight, and probably most importantly is that you learn a lot of problem-solving skills during your 4 years at school, and that's really what people in the industry are looking for now.
Virginia Tech's mining department gave me the opportunity to have 2 summer internships leading me to secure my position here at Vulcan full-time.
Having a mining engineering degree from Virginia Tech has given me the opportunity to build professional relationships and find creative solutions to problems facing the mining industry.
I would say the network is definitely the biggest thing that the degree has brought me, and it's amazing to see who you'll run into halfway across the world who still says go Hokies.
Virginia Tech has a wonderful reputation, and no matter where you are in the country, everybody knows where you are. Everybody knows Virginia Tech. So
the degree itself does take a lot of work, but it's well worth the effort.
The skills I learned in the mining engineering program and now Geotechnical training were more than adequate to be successful. At least once per month, I still reference old notes or PowerPoints from my time as a student in the mining engineering program. This department will set you up for success for the rest of your life. Once you make the decision to become a mining engineer, you will never regret it.
Because I use the geology and engineering principles that I learned in school every day. I'm glad I chose mining because it was a lot of fun and it opened up a lot of opportunities for me.
A degree at Virginia Tech is what got me this job. It proved to me that it's just as important what you know as who you know. This was one of the best decisions I've made, never looking back.
Virginia Tech helped prepare me for this career by exposing me to a wide variety of mining techniques and support systems, as well as training me in the modeling of those systems so I can provide the lowest cost solutions for my company.
The opportunities the mining department offers are endless, and we hope to see you out here in the field one day.
Go Hokies!
Go Hokies!
yeah, go Hokies!
And go Hokies!
Go Hokies!
So not just that, they're home to a lot of different student organizations, right? We've got a Burkhart Mining Society where almost everyone's members. They plan trips, they do different things. We go to different conferences. So we typically send students to Denver or Salt Lake or something for the annual mining conference. There's a big one in February. They do a lot of different activities within the sort of the Burkhart Mining Society. We do a lot of stuff with professional development. We host our own career fair at Tech. If I can go backwards, we host our own career fair at Tech. We bring in companies. We've got a mining competition team that goes out and does sort of old skill mining. We've got academic competition teams that go out and design mines for competition. We have a mine rescue team that goes to competitions as well. We do a lot of different community service activities as well in the department. Field trips. This is an underground mine here. We do more field trips. Try to get people underground to surface operations. There's lots of social activities that go on within the department. As I mentioned, it's pretty close knit. So that's mining as a whole. I see another question, I think. Space mining. There's a good one. Yeah, we've had a project. We had a couple professors, Dr. Aaron Noble, Dr. Michael Karms, Dr. Mario Karfakis had a program funded by NASA to look at mining on Mars, right? So designing systems. In this case, I think they were trying to mine water. Actually drill and produce water underground. So we'd have to take this frozen material and bring it back to sort of the base station. So yeah, we've had some work there. We've actually put, as a senior in mining engineering, you have to do a senior project. It's typically a mine design project. You do it from the exploration to the reclamation, all the way at the end of the life. You're designing a whole mine over a year period with three other students working with you. But we have had other projects where we're working with other engineers on it's called a NASA, I think a nice NASA Ice Challenge, designing equipment to actually go onto Mars and once again drill and recover material. And they went to a competition down in Houston at NASA. So we put mining engineers on those teams multiple times. So they were university teams. So yeah, there is definitely some work going on there with potential for space mining, asteroids, those sort of things. I'd say most of the focus has been Mars. If you're looking to colonize Mars at some point in time, we are going to have to mine materials there and use them there. So that's been a lot of the focus. I'm not sure asteroids has been as big a focus within our department, but people are looking at that. So hopefully that answered your question. Any other questions? Well, if not, I appreciate your time, you guys showing up here. If you do have any questions at any point in time, you can email me, nino@bt.edu. If you end up on campus, want to come see it, we're building a brand new building. Mining engineering is going to be hosted in there. I think it'll be open when you guys arrive here, or it's going to be open in the next year. We're going to put a mock mine in there where we're able to do some different mining work within this building. So we're really excited about that. And if you ever have any questions, feel free to just reach out to us. We're a pretty open department. We'd be willing to just sit down and chat about options in mining.